Okay, guys, welcome back to MedZone African Motives. We are still on our electrotechnics info, working with the DC machines. So this is a most important part of a DC generator, whereby they are going to ask you questions on the open circuit characteristics of a DC machine, considering a DC generator. If you're to consider this part, we like almost each and every question paper that you have, you're going to like, there's this part. Not like everybody, it's just like maybe they skip one trimester on another trimester. This question is there. So you need to understand actually the basics or the properties that we are going to have on the open circuit characteristics. All right, consider a DC generator. Okay, we are all this part that is on a DC generator. If you are to consider this, I want us to consider when we are given a shunt. All right, remember a shunt excited generator. Okay, a generator supplying current. So we are going to have the shunt field, and at the same time, we are going to have the part of the armature. So this is what you're going to have. Remember your voltage. This is the generator supplying the current. Okay, so we have got our armature current, and in this case, we have got the shunt field current, where this is the shunt field, also having the generated EMF, and also considering that this is our armature, where we are also going to have the armature resistance. Okay, so considering this part, actually, there are so many things that we have. I'm not gonna talk about much or a lot into this. We know that when we are considering or when we are working with a shunt generator, the generator is supplying current at the end, which is fine. Due to the resistance, because we are saying if the resistance of the field, it is going to be reduced, maybe there's a change in this resistance, it is going to affect even the voltage that we have at the end. So you'll be given the open circuit characteristics. You are given open circuit characteristics. On the open circuit characteristics of a DC generator, we are going to have the EMF, which is on this side. So this part we are referring to the EMF, which is the terminal voltage. Okay, so you talk about the terminal voltage. And you are going to have the field current. So let me explain with this, maybe we can understand. So we are going to also have the field current, which is in amperes. Remember, this is voltage in volts. Okay. So as the current is increasing, the terminal voltage is also increasing. So it increases like, let us just say we are considering something like there's an increase as the current is increasing, the voltage is increasing, until a condition that you see that the voltage is no longer actually like the increase is there's a slight increase. It raises to a certain value where now the EMF starts to fall. So at a certain value that is build up of the shunt resistance. At that value, we are going to notice that maybe we are considering somewhere at this point. The increase is going to be very, very low. Like if you are to even to continue with this, it's going to be down. So the question is, how are we going to locate the point which is representing the open circuit voltage? This point is given from, because you remember when dealing with the open circuit characteristics, you're given the speed, this and that, everything is there. So having the shunt resistance, remember, we've got the shunt resistance that we are referring to in all this. How were you obtaining the shunt resistance before? That is the question. The shunt resistance, we're taking it to be equivalent to the voltage over the shunt current. So meaning in the same sense, if you are to consider this shunt resistance, which is the resistance that you are given at the open circuit, maybe you're given the resistance of the field. We are considering the shunt resistance, the resistance of the field. From the concept of having the voltage over the current, meaning to say it is representing the change in voltage over the change in current, which is the field current. Guys, let us go back to our mathematics. The change in voltage over the change in current, it is actually representing the slope, the gradient. Remember from the gradient concept, the change in y over the change in x. Y is representing the EMF. So this Y is representing the EMF, X, the current. So meaning to say from the resistance that you are given, you are taking that as your gradient. So you can determine the gradient taken from 0, 0, because at that moment, we are going to start at a condition when the terminal voltage is at 0 and the current is at 0. So you have an initial point that you can use to determine another point that you're going to use to, remember guys, you need to have a line, the steepness of the slope, the line. Given 2 points like this, they're enough for us to draw a line. So to draw a line, you are going to consider the gradient concept. This is from our mathematics now. The gradient, the slope. So let's say I'm given a 3. The gradient, meaning to say the change in the voltage over the change in the current, must give a 3 as just like a gradient. So if I'm given the point 0, 0, what I just need is to have another point where I can obtain the gradient of 3. So the gradient of 3, guys, 3 over 1, it gives us a 3. So meaning to say you can use that sequence and so on and so on and so on. 3 over 1, meaning to say in order for you to have 3 over 1, it is a point which is written as 1, 3. Remember the change in y over the change in x, voltage. So 3 minus 0, that is 3. 1 minus 0, that is 3 over 1, which is going to give us the 3. So you can use that now as a sequence to obtain points which are clearly presented on the graph. You do not just work with a point where there's a decimal. Choose points which are visible, okay? You mark that point. Then with the point that you have, you can join through the 2 points from the 0, 0, passing the point that you are given, which is the one that you indicated from the gradient concept. So this point and this point, they helped you to draw the line They are not as important. They're just helping us to determine or to have this line. What is important is the intersection of the line that we have drawn, which is the slope representing the gradient, which is the field resistance. At the intersection with the graph that we are having, at that point, that is where you have got your open circuit voltage at intersection. At the intersection. So once you understand this, you guys are done. So it's all it's a play around of for our mathematical calculations. So I'm gonna explain this so that you understand me on this question. We are given this part, question 3.1. So these 10 marks, guys, is just 10 marks. Just take these marks just like that. They are direct. So only that the challenge that we have is that these typical questions and the graphs that we are having, they are not suitable for these typical questions. So at the end of the day, you'll find out you are having your answers as approximate values, approximated to a certain value, not exact. You're not, yes, you can have exact values, but in other conditions, you'll be having an approximate value because of the graphs that you remember, you're drawing on a graph using freehand. So the smoothness of the graph also affects our answers. So that is where I'm talking about the approximate part. So they are going to consider that because the graphs that we are using, they are not exactly the ones that are supposed to be used when answering these questions. I'm going to explain that. All right, the open circuit characteristics of a shunt excited DC machine are as follows: the terminal voltage and the field current. So like I was explaining on the diagram, you take note, this is the part of the terminal voltage and the field current on the x-axis. So meaning to say you consider that, okay, on your presentation. So the question is, from this information, plot a graph and determine. So let's start by plotting the graph before we determine anything. All right. So you're going to take these values. Remember, it is like this. This is the field current and this is the voltage on this side. So you take these values here on the x-axis, the 2, 4, 6, and so on the x-axis on the field current. So we are going to have, as you can see, it's 2, 4, 6, and so on. So we can take this x-axis. This will be our field current, all right? So this is our field current. So I'm just gonna write IF, or you can just write field current. All right, field current. That is our field current in this case. Okay, so we have got our field current in amps, and this side we are going to talk of the terminal voltage. All right, so this is where you are going to have your terminal voltage in this case. All right, which is measured in volts. So according to the current, we saw that is 246. So the suitable scale that we can use is the 2468. So you can choose 2 centimeters to represent 2 units on each and every box. It represents 2 units. So that's 2 for 6 and so on. All right. So guys, let's just hope this network is not going to affect me. It's 2, 4, 6, 8, 10, 12, 14, 16, and so on and so on. All right, so you can even give an allowance of 18. So this is on the current, which is the field current. Then we move on. Let's go back to the voltage. According to the terminal voltage, 20, 40, 50, and so on. You can choose that 20, but if you choose 20, 20, 40, 60, it's just going to be like 3 boxes. So just to give an allowance, you can choose even 10, 20, 30, 40, 50. At least you separate your points so that at the end, your graph is clear. At the end, you must have something that is clear. So we can choose 0, 20, 10, so that we can at least accommodate points 0, 10, 20, 30, 40, 50, think up to 70 there we can have our values 50, 60, 70, 80, and so on, according to the maximum value that you are having here, which is 62. So we can just take up to 70. We can accommodate the 62. So this is how you're going to mark your points. It's 2 versus 20. 2 on the current versus 20 on the voltage. So the current is 2, then that is 20. So as we can see, guys, the point 220, it's a point which is clearly presented. That is 2 versus 20. The current is 2. The voltage is 20. You mark your point, current 2, voltage 20. Where they meet, you mark a point. So that is it, guys. You're going to mark this 4 versus 40 and so on. 4 versus 40. When the field current is 4 somewhere there versus 40, mark your point. All right. Another point, 6 versus 50. So that is 6 on current versus 50. And we can see this is also clear. 6 versus 50. Okay. Then we move on. 10 versus 58. 10 versus 58. So we want 58. So 58, according to each box, these are 10 boxes within this box that you are given. There are 10 small boxes. These small boxes that you are seeing, there are 10, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 boxes. So according to this scale, these small boxes, 10 of them, they are representing 10, 50 to 10. There's a difference of 10. So meaning to say 1 box represents 1. So it's going to be like 51, 52, 53, 54, 55, 56, and so on. So we need the point. Remember, it was 10 versus 58. So 58 is just 2 boxes from 60. This is 60. Here, this is 60. So you're going to need 2 boxes going down, 59, 58. So, okay, guys, sorry for that. I'm supposed to be here. 10, 60 there, 59, 58. Remember, this is 10 versus 58. So you must, guys, what is happening? Is this 10 or is this 8? This is 10, not 8. I'm actually in the right direction from the first part here. It was in the right direction. This is 10. So this is 8, 10. So we are going to skip a box there. We are skipping 1 box to 10. So this is 10, guys. 59, 58, somewhere there. All right. That is 10, 58. Okay. You do the same thing. Just up to the end, 13 versus 61. 13 versus 61. So 13, it's in between 12 and 14, in between. So you're going to count 5 boxes, but against 61, remember here, 61, it is 1 box from 60. Okay, so 12, remember, I say this is, let's go back, guys. This is 13. So I said it's in between the 12 and the 14. 12 and 14 in between, then 61. So you're gonna need 5 boxes. 1, 2, 3, 4, 5. That's in between, then 61, somewhere there. So guys, this is what you're going to do. You mark all your points and so on and so on. 15 versus 62. 15, again, 15 is in between 14 and 16. Then 62, you're just gonna count 2 boxes up. 1, 2, 3, 4, 5. That's 15, 61, 62, somewhere there. All right. So these are the points that you were going to have at the end. So these points, you join them. Remember, you have to plot the graph. So you're going to join smooth. That is where you're supposed to be very, very smooth. You must have a smooth graph. So in this case, as for me, guys, it's gonna be difficult. Remember, this is software, guys. So to be smooth as it is supposed to be. It's going to be difficult, but I just hope you are going to draw a smoother graph. It's not supposed to be like this, guys. This is not as smooth. It's supposed to be very, very, very smooth so that your answers, they are in within. The answers are supposed to be in within. All right. So with a smooth curve, like the one that you are going to have, this is what they wanted. Okay. That is to plot a graph. Then they are saying, and determine 3.11. Okay. This is where now that part that I was explaining before. The voltage to which the machine will excite no load. This is at the open circuit characteristics. When it excites a no load, when a shunt connected, okay, when shunt connected, remember this is a shunt machine, when shunt connected, if the total field resistance is 5 ohms, the total field resistance, remember here, the change in the voltage over the change in the current concept. So you are given this, that the total field resistance is 5 ohms. So this is what you're going to do. You have got the resistance, which is 5 ohms, which is the shunt field. So this is 3.11. So what we need is the open circuit voltage. At that point, we do not know, but we are given the field current, which is 5 ohms. And I said, this represents the slope, the change in voltage over the change in the current, which is the field current. So meaning to say, in order for you to have a 5 ohm, always, like I said, starting at 0, 0, you're going to use the slope concept. You use the slope, the gradient concept. Guys, how you determine gradient from a graph? These are the points. So you've got the point 0, 0 like this. This is the first point that you use. So to obtain this slope, which is 5, let us just say, because it's voltage over current. So if your voltage is 5 and the current is 1, you are going to obtain a 5. This is the 5 that you're given. So you can use the value that you're already given there. 5 over 1 is equal to 5. So according to our scale, remember, this is voltage over current. So if voltage is 1 and the current is 1, the resistance is going to be 5 ohms. This is 5.1. So if you are to locate that point, 5.1, you mark it. It's fine. You use that to mark that point. But just because, guys, the 0.51 is so close, so this is what you do. According to the scale, this is 10, 20, 2, 4, 6. So as long you are with those points, 10, 20, and so on, guys, if you are given a gradient, let's go back to our mathematics a little bit. If you are given a gradient of 5 like this, it means like 5 over 1. This is in your hands. You can do whatever that you want with this. You can multiply this by 2 over 2. Multiplying by a number over that number does not affect anything. So it means 5 times 2, that is 10 over 1 times 2, which is 2. So we've got 10 over 2. 10 over 2 gives us 5. You can do whatever that you want. 5 over 1, you can multiply by 3 over 3. 5 times 3, that is 15 over 3. So multiplying by these numbers, it is just for you to obtain values which are at least visible on your graph and not close. They're not supposed, just avoid to be close to the 0, 0. So this is what you can, so you can use any point, guys. This is what I'm trying to say. So let's say you multiply by 2 over 2. It means you've got 10 over 2. The voltage, remember, the field gradient is the field current. So it means the gradient is the voltage over field current. So it means you've got voltage over current. It's a point, that one that you can mark on the graph. Remember the points. If this was X, and this was Y, you have a point as XY like this. But this time X represents the field current. Y represents the voltage. So in this manner, if I understand this, that it represents the field current is X, it means this field current here is 2, the voltage is 10. It's a point. I can mark this point. Guys, you can, as long you are multiplying by a certain number over that same number. Let's say I choose to use 10. This was 5 over 1 times 10. Let's multiply by 10. 10 over 10. 5 times 10. That is going to be 50 over 1 times 10. That is 10. It means this is the voltage. This is the current. So the field current, as we are marking the points, remember the points, field current to voltage. So the field current is 10. The voltage is 50. Guys, these points, including the point 0, 0, they are going to help you to draw the line, which is the slope, representing that slope. So already you marked your point 0, 0 like this. You were supposed to mark the point 5 versus 1, but it's too close. Too close. So let's use another point. You can just, guys, I'm not saying if you were using that one, it was going to be wrong. No. When the current is 2, the voltage is supposed to be 10. 2 versus 10. Let's mark 2 versus 10. So if you check the slope, 10 over 2, it gives us a 5. Thus we have got that 5 ohms. Another point, you can 2 points there now, but you can even mark 3 points. The current, when it is 10, the voltage is 50. 10 versus 50. The current is 10, the voltage is 50. You mark this point. These points are the ones that you use to draw the line, which is going to intersect with the graph that you are given. That is how you answer this type of a question in order for you to have that open circuit voltage. So joining from the 0, 0 using your ruler, passing those points, which gives you a gradient of a 5, a slope of a 5, passing through these points, as you can see like this, you are having the slope of 5 along this, like any part as it is along this part, the gradient that you are having along this line is equal to 5. And that gradient, it is the field resistance. Remember, I said this. So at a no load voltage now, this is at the intersection, like I explained here. Let us go back to that introduction part. Let us consider this so that we finish up. So here I explained at the intersection, that is where we have our no load voltage, which is the open circuit voltage. So meaning to say we need the intersection where these two graphs intersect. They intersect at a certain point. Where they intersect, that is where you are going to consider. All right, so they're intersecting somewhere there. That is at according to my graph here, that is at 60 at the intersection. This is the voltage. Remember, you need the terminal voltage. So at the intersection there, the voltage is 60 there at the intersection. You need the voltage. So that is your E naught at 60. So that is the idea, guys, of this graph. And if you check down there at 60, it corresponds with what? At 60, if you're to take it down, the current there is 12. But we are not asked about this. But if you're to take it down like this, the current there is equivalent to 12. So what we need is the voltage. The question was on the voltage. So all this was in order for you to have that slope. So therefore, our E naught is equal to 60 volts, which is, you can even consider if you want current times the resistance. Remember our resistance there, it is 12. So 12 times 5 is equal to 60, as you can see. But you're supposed to take it graphically at the point of intersection of the two. So this is how you attempt these typical questions, guys. So you need your graph, and you also need the line representing the shunt field resistance, which is the slope from the voltage over the current. So this is the gradient concept from your mathematics. You're applying your mathematics on that case. All right. Then we move on to the other question, which is about the critical resistance. So for the critical resistance, this is the one that you obtain at the tangents of the curve. So on this curve, where we can have a tangent, remember a tangent is a line that touches the curve at a certain point. So the tangents on this one, guys, it's gonna be difficult for me to explain the part of the tangent, but remember your mathematics, guys. If you're given a curve like this, the tangents, you draw it with you take a ruler. Guys, this one, it wanted me to be like having to show you like I'm having, what can I say, a direct video, like, because this part, I don't know if you're gonna understand. This is the idea of a tangent. The way that you draw a tangent, since our curve is like this, meaning to say you place your ruler in this manner, you move with the ruler until you meet a point like where you are going to, where it meets the curve. That is where you are going to have your tangent. That is the idea of how you draw a tangent. So you're going to place your ruler something like this according to our curve. Then we move towards the curve with the ruler. You are going to move towards the curve. So our curve is something of this nature, guys. So if you have to consider, this cannot be at tangents. So you can shift a little bit. Okay, this cannot. Let's shift a little bit here. So if you check here, it can be a tangent. It just meets the curve at one point, supposed not to intersect twice, but it's supposed to be at one point. So here, guys, it's difficult for me to rotate, but as you can see, if you move like this is the tangents. Okay, so from this concept, you can even consider this way. Okay, this line that you're already having here, just move with it like this. Okay, so it's not supposed to intersect like this one, just supposed to move a little bit. You see, if you see, okay, if you close there, it is not intersecting at this point. Okay, it does not intersect. So this is the tangent. So this is also, it is the part of the smoothness of that graph of yours also, because if you draw something like this, or maybe it is like this, it is going to be difficult for you to have a tangent, because it will end up like entering the other part of the graph, while at least you're at a right point, but because of your graph. So that is where I was saying, let your graph be smooth. So this is how you find the critical resistance, it at the point of tangent. So this is our point of tangents. At the point of tangent, which is the point of tangent in this case, this point here, which is at the tangent, guys, what are you calculating? Okay, let me go back to you. This is resistance. How are you calculating the resistance, the change in the voltage over the change in current, voltage over current? So meaning to say, I need the voltage and the current. The voltage and at that point, at that point of tangents, that is what is the voltage there? The voltage at this point corresponding horizontally. This is where you find your voltage. The voltage corresponds with 40. Going vertically down straight here at this point of intersection, if you're to consider it down straight, this point was going to correspond at 4. That is how you determine this. So at the point there, resistance, voltage over current. So that's 3.12. So meaning to say our critical resistance from the voltage over current, it is going to be the voltage of 40. What is the current at that point? The field current is 4. So this is going to give us the critical resistance. That's the critical resistance was going to be 10 ohms according to our function. This is what you're going to have. So this is how you answer these questions, guys, just like this. So make sure your graph is smooth. The smoother the graph, you're going to see that you're not going to have any challenge. All right. So I'm going to use the same graph to answer another question so that we do understand a little bit. So these are like 10 marks, guys, a lot in exam. The open circuit characteristic of a shunt excited direct current machine is as follows. The terminal voltage, the current. So again, guys, we're going to choose a suitable scale, plot the graph, and determine the following. As you can see, it's just one and the same as what we had before. So we are going to have a suitable scale on the field current. This is 0.6, 1.2. So we can choose up to 3. You can even choose 2 centimeters to represent 1, so that at least we do not have challenges like to locate the decimal 0.1, 0, if you use this one, remember these are 10 boxes. Remember what I said? These are 10 boxes that are on this line. So considering 10 boxes, you can say 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 8, 9. Then that's a 1. So meaning to say, using a scale of 2 centimeters, 1, and so it's best. Okay, like those 10 boxes to represent 1. So on the field current, we're gonna have 1. So if you saw the bigger value there, it was a 3, something, 3.4. So you're gonna just maybe mark 1 up to 4. 1, 2, 3, 4. All right, something like this. Let's check what we have on the voltage. So the voltage is 50, 150, and so on. So we can even use the scale of 2 centimeters or those 10 boxes to represent 50. After each and every 10 is going to have a 50. So remember, this is your terminal voltage. Okay, so this is our terminal voltage, this side. Terminal voltage. All right, so that is, we can just try to use the 50, 100. After every 50, we add, that's 150, 200, 250, up to, if you have to consider, 220. So we can accommodate up to 250. So meaning to say, let's analyze our scale first. Let's analyze our scale first. According to our scale, I talked about this in the field current, which is our X. This is like 0.1, 0.2, 0.3, 0.4, and so on up to 1. What about in the voltage, which is the Y-axis? It's like we are representing this as 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. So one box, it's 5. 2 boxes, it's 10. So when you see 2 boxes like this, that's a 10, 2 boxes. Okay. On this one box, this small box, it represents 0.1. Analyze your scale. Analyze it, because you are going to use it to mark these points. So analyze your scale first. Okay, so as we saw, guys, previously, we're just going to mark our points. The current versus the voltage, 0.6 versus 50. So when the current is 0.6, the voltage is supposed to be at 50. 0.6, that is 6 boxes. Like I said, 0.1. So we need 6 boxes, like 1, 2, 3, 4, 5, 6, but against 50. So that's 1, 2, 3, 4, 5, 6. Somewhere there, you mark the point. That's 0.6 versus 50. Okay. Then again, we've got, oh, sorry for that, guys. I'm going back to this one that we talked about. Let me just remove this so that I do not end up like what I did in another video, ending up using that question, which is not the one. All right, so the other point that we are given is you're going to have those points and so on up to the last one. Okay, guys, let me try to have this. That is 1.8 versus 150. 1.8 on the current. That's just 2 boxes before 2. Then 150. Remember what I said, 2 boxes represents 10. Okay, so 150, let's say this is 2, 1,9, 1,8 here. So it means 2 boxes. That means we have got a 10, which is 60, 2, and so on. But there we need, take note, what we need is 150. So we must consider when we are at 1, we need 150. Okay, so let us be at 100, somewhere around 100. Already 150 is there. Sorry, guys. 150 is already there. So 1,8 just going to be 2 boxes before 2. That is 2, 1,9, 1,8. Somewhere there, guys. 150 is already there. You see this, guys, because of that thing that I was checking before. Now I think I'm on that other graph. Anyways, that is 2,6 versus 190. 2,6, 190 we do not have. So 190 is just like 2 boxes below 200. Remember, 2 boxes then 10. So just 2 boxes before 200. Then the 1,6. Okay, so we need the 1,6. The 2,6, I mean, the 2,6 is just from 2. You are going to count 6 boxes from 2. Remember, each box is comma 1. So 6 boxes from 2. Then it's somewhere here. That is gonna be, all right. So I need 1, 2, 3, 4, 5, 6. Then going down, 2 boxes going down somewhere there. That is at 190. Then this is 2,6. Like we say, 2,1, 2, 3, 4, 5, 6. All right. So that is it at this point. So make sure you mark your points correctly. The following point, it was 3,3 versus 210. So 3,3, just 3 boxes from 3. We need 3 boxes from 3. 1, 2, 3, then 210. That is 2 boxes from 200. Remember, 2 boxes represents 10. Another part, it was going to be 3,8 versus 220. So 3,8, these are just 8 boxes from 3, or just maybe 2 boxes from what? From 4, but versus 320. So this is 3,8 somewhere here. Remember, this is 310, 2 boxes. You count again 2 boxes up. So somewhere there, you mark the point. So this one, it was going to be close, the points, the way that they are, but that is what you're going to have. So make sure you mark these points up to the last one. Okay, up to the last point, we have marked our points. Then we join these points smoothly. Like I said, this is supposed to be smooth. Okay, so we are going to join our points. Make sure this is smooth. Okay, something like this. So this is what you're going to have at the end. But guys, yours is supposed to be smoother than the one that I'm having here. So the question is 4.31. What we need is to determine the voltage to which the machine will excite on no load. Again, when shunt connected like what you're given, if the total field resistance is 70 ohms. Remember, we are at no load, which is at open circuit characteristics back, but the field resistance is 70 ohms. So like I said, the field resistance is the slope. The field resistance represents the slope. So I hope you understand me here. So this is 4.31. So we are given the field of 70 ohms, which represents the slope, the change in voltage over the change in current. Okay. Already we are given a 7, and I said this must be taken from 0, 0. So already you've got an initial point to consider on the slope, which is your gradient, the point 0, 0. Okay. The other point that you are going to take is that at 70, to have a resistance of 70, it means the voltage must be 1 and the current, the voltage must be 7 and the current must be 1. 70 over 1. But the question is, are we having this point exact where we can mark the 70 and the 1? Okay, when the voltage 7, when you say we need 1 versus, if we can have that, it's fine, we can mark. Okay, guys, this is enough. This part here, this is it, guys. Like I said, this is the change in x, the change in y over the change in x, but the point is written as xy. This is your y, this is your x from the change in y. So meaning to say we have got like x value, to say x is 1, y is 7. But this x represents the current. The y represents what? The voltage. So if you can mark this point, guys, that is 1 versus 7. When this is 1 at this point, 1 versus 7, and you can mark the point 7. 7, it's according to our scale, remember 2 boxes, it's 10. So 50, that is 50 here. We're going to have 60, 70. That is at this point. But this point is just close to this point. So you can choose another point as long it's visible, that point, as long that point is visible. So what can you do? These currents are multiples of 2, like 1, 2, and you can even use 2, 4, 6. So we can even multiply by 2. Let's multiply by 2 over 2. Like I said, what you multiply with must be both numerator and the denominator. 70 times 2 gives us 140. 1 times 2 gives us 2. Just like the same way, this is your y, this is your x. So x is 2, y is what? Is 140. Just like x and y. So if x is 2, meaning to say we are on the current 2 versus 140. So maybe 140, guys, is going to be just 2 boxes from what? From 150. Remember, 2 boxes, they represent 10. So this 150. Just like that. You can even mark points, 3 points, 4 points, and so on. These points, they are not, they've got nothing to do with this graph that you have drawn here. These points, they have to do with this Cartesian plane of yours, which is your graph of yours, with the gradient concept. Already, you have a reference 70. 70 over 1 is your gradient. Play around that. If you can mark that point 70 versus 1, which is 1 versus like this, if you can mark it and it's clear from your graph, join from the 0, 0, you're done. That line, it is going to intersect with your graph. So this is it. So these are the points that we are going to mark from 0, 0, this point, and this point. So if we were to mark these points, guys, let's see what we are going to have at the end. If we were to mark these points from the 0, 0, it was going to pass here like this. So it's something like this, guys. Okay. Yeah, something like that. So this is what you're going to have. So also just make sure that your graph is smooth, guys. If it is not that smooth, it is going to affect your answers at the end. So that is where we are going to have our voltage at the point of intersection. At the point of intersection. So these two graphs, they are intersecting somewhere there. This is where they are intersecting somewhere there. At that point of intersection, that's where we have the open circuit voltage. So as you can see, this point here is somewhere there. Okay, that is, remember, 2 boxes, they represent 10. So this is 190. So 1 box, it's 5. So it's at 195. So if you have to take this corresponding, it corresponds at what? At 195. So that is our open circuit voltage. It is at 195. It's an approximation that we are having. So it's at 195. So maybe according to the exact value, it can be 196. I do not know. I think it was 196. But according to mine, guys, this is 1. So that is where the smoothness of the graph, and where I was saying that this type of a question is not fair enough, because you can't see that this is 1,6. This is exactly 1,6. It can't. So these graphs, they are not suitable for this type of a question, but it's an approximate that you are having. So you're going to have it as an approximate like that. So that is your E naught, which is the open circuit voltage at these conditions. So that is where that line is playing a role. So this is at 195. So the other thing is that, are we going to have the 70 ohm? All right. If we are at this point, I do not know. So what's gonna so what's up is something like 196 there. So guys, the smoothness of the graph there, it plays a role. All right. So that is what we have according to our graph, but it's supposed to be approximately 196 or something like that. So guys, the smoother the graph, and like I said before, even if your graph is smooth, to take that exact point takes your time, because you are not going to have exactly the value at that point. You can see that, guys, this is 197, or so, but they are going to mark that answer that you're going to have. Okay, so that is what we had. Then the other part, it was on the critical resistance. Just like the previous case that we had, we are also given the part where we need to find the value of the critical resistance. So like I said, this one, we are going to need a tangent. We need to draw a tangent to the curve. So this one, you need your ruler, and you must be close enough, like the line, the way that you place your ruler, like this way, like I explained before, it must be closer enough where you can see the tangent somewhere there. So because of the smoothness of our graph, yeah, we can see this somewhere there. This cannot intersect with another part at another point. It's not, remember, a tangent is not supposed to intersect twice. So a little bit. So the smoother your curve is, that is the approximate that we're gonna have also on our answer. So something like this, okay? Something like that. So it was gonna approximate. It was actually approximating according to these guys. It was gonna be difficult, but according to the exact value, it was approximating at 100, and this current, the current there was approximating at 1,1. So I do not know, guys, what are you obtaining from your graph? Let me know from your graph what are you obtaining. But from the exact measurement that I had before, it was approximate, it was at 100. So RC is 100 versus the current 1,1, and that was going to be 90,909 ohms at the point of tangents. At the point of tangents. So let me know, guys, from your graph what you are obtaining, because here, guys, I might prepare something, but on the presentation, these softwares, they might tend to be something, but I hope you do understand the idea of the question. So this was our part. We're gonna have another part, which is very important, where we are going to relate the speeds, relating the speed this time. So we are given the open circuit characteristics of a DC shunt generator running at, we are given the speed originally it is running at open circuit characteristic, it is running at 600 revolutions per minute. So you've got the current 1, 2 up to 10, the terminal voltage, and so on. So we asked these cases the speed, okay, to determine the voltage to which the machine will build up, just like the previous case. 2.21A1, it was the speed. If, okay, let's consider this. If the speed is 600 revolutions per minute, if, meaning to say we are still at the 600, nothing has changed. We are still at open circuit characteristics. At no load, nothing has changed. We are still at the same speed, nothing has changed. and the resistance of the field is 84. So if you check, this question is just like the previous case. We were at the same speed, nothing has changed. It is the same thing as what we are having on this condition. The speed is still the same. So you're going to mark your points. Okay, let's analyze, guys, our current 1 up to 10. We are going to need that graph again. Whether you are asked to plot that graph or not, you're going to need that graph, okay? As we saw, it is that intersection. So we need the graph, okay? So our field current, as we saw, it is 1, 2, up to 10. So you can even use a scale. Those small 10 boxes present 1. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Then on the voltages, we are given, let's consider and see what can be the best scale that we can use. That is 100, this and that, up to 640. 6 boxes. So you can use it even 100, 6 boxes, they are fine. Okay. So on the terminal voltage, which is given there as the EMF, that is our terminal voltage, we can just use 100 each box, like each complete box, that is 100, 200, 300, and so on. Okay, so that is at least a suitable scale that you can use. 400, 500, and so on. Okay, that is 500, 600. We saw that it was approximately 620, so at least we need something like 700. Okay, so can even add, because there are going to be 2 graphs, so we need to add. We do not know where it is going to end. Let us even add another one. That is going to be 900. So these are the voltages, okay? So the first question, it is a direct question, just like the previous one. You are going to mark your points, then you consider where the slope of the line meets the graph. That is where you have got the voltage. So you're going to mark this one already, the current is on top. So it's this way this time, 1 versus 100. The current is already on top. So it's 1 versus 100. The current is 1. The voltage is 100. So you're going to mark these points and so on up to the last point, guys. All right. So I'm not gonna take much time, guys. Let us just mark this up to the last point. 2 versus 260. So 2 versus 260. So 260, that is from 200. We need 6 boxes. This is like 10, 20, 30, 40, up to 100. Remember, there are 10 boxes that we are talking about there. So 2 versus 260. We're going to count 6 boxes from 200. 1, 2. That is 1, 2, guys. Okay. That is 1, 2, 3, 4, 5, 6, somewhere there. So, guys, let's hope you understand. All right. The other one, it was 3 versus 390. 390, that is just 1 box from 400. Okay. Another part, it was 4 versus 470. That is 3 boxes from 500. 1, 2, 3, somewhere there. 480. 490, 500. Yeah, 3 boxes. Okay. Then that was then 6 versus 570. 6 versus 573. Guys, I mixed. This is 4 versus 470. 4 versus 470. Okay. Then 5 versus 530. 5 versus 530. 530, that is 3 boxes from 500, 10, 20, 30. Okay. Then it was 6 versus 570. 570, which is 3 boxes from 600. 1, 2, 3, going down. Okay. Another point, it was 7 versus 600. 7 versus 600. 8 versus 620. 8 versus 620, that's 610, 620. Okay, 2 boxes. 9 versus 630, which is 3 boxes from 600. 1, 2, 3. 10 versus 640, which is 4 boxes. 1, 2, 3, 4. Something like this. So this is what you were going to have at the end. And with this, you're going to draw your smooth graph by joining these points. All right, so as for me, it's gonna be difficult, guys, like I said before, but you are going to have something like this. Okay, something like this at the end. So it was gonna be approximately something like this. Okay, so this is your graph, and the question is, we are supposed to have the voltage. Like I said, the speed is still at 600, nothing has changed, but the field current is 84 ohms. I mean, the field resistance there is 84 ohms. All right, so that's 2.21. So remember what I said, the field to be 84 ohms, that is the change in the voltage over the change in the current. So meaning to say exactly, or originally you are at 84 over 1 to obtain this 84. From the 0, 0 that you are having here, you are supposed to mark 84 versus 1. Guys, if you can locate this point of 84 versus 1, it's up, you can mark it. But as you can see, guys, this is like one box, it represents 10. Like this is 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So if this is at 84, it is difficult to mark the 84. It is difficult. It is very, very difficult, because this is like you are having an 80 here. Where is 84? You see now that part I was saying, our graphs, they are not suitable, but they are graphs which are, they are exact graphs. So we just hope with the time frame, we are going to have those graphs in simplification, so that at least we can understand what I'm trying to say. So since this 84 is difficult to locate, so you choose, you now, according to scale, 100, 200, 300, like that. Like if you check, these are like multiples of 10 and so on. So you choose like which number can you use. If you multiply by 2, this, guys, this is where your mathematics plays a role. Already you've got the point 0, 0. You just need to mark another point which is visible. So now you're trying to locate a point. It was supposed to be 84 and 1, like I said, like y and x. So it was supposed to be 1 and 84. It is difficult for us to mark the point 184. So we are just looking for another point that we can use. So if I multiply by 2, what was going to happen? If I was to multiply by 2, it was going to give us 168 over 2. You multiply by 2. 168, according to that scale of 100, 200, it's difficult again also to locate. So multiplying by 2 over 2 is not helpful. So let's choose another number. Let's multiply by 3. Hey, guys, it's going to be difficult. 4 over 4. So if you were to multiply by 5, if you multiply this by 5 over a 5 like this, I want you to see what's going to happen. So you try, guys, until you get a number which is visible. In case that the point is not visible, other points like previously, they were visible, but this one is not as visible. Okay, let's multiply by 5. 84 times 5 gives us 420. So it's 420. 1 times 5 is 5. 420, it's easier to locate because I was explaining each small box represents a 10. So it's easier for us to locate 420, because from 400, we just need 2 boxes from there. So this one, it's easier for us to locate. So you choose the number that you choose. It must be that number over that number, guys. Let's say you are going to choose another number and it gives you a point which is visible. The line that you're going to draw and the line that I'm going to draw, they are going to pass through the same points. Do not worry about that. So as a point, instead of me using this one, which is not a clear from the points that I'm having because of the decimal concept, I can use this one. Again, the concept does not change, just like the change in y over the change in x. So this is the x value, which is 5. The y value, which is 420, representing the voltage. So we can mark this point 5 versus 420. Let's see where this point is. When the current is 5, we need 420. Remember the XY concept. So this is 5 here. 5, 420. We need 2 boxes. Remember, each box represents what? 10. So 2 boxes. This is 410, 420, somewhere there. This point and the point is 0, 0. They are enough for us to draw this line to represent the slope. They are enough. These 2 points from the 0, 0 like this, joining to that point, it is enough. That's the concept. It is enough. So this is what you're going to have. So the line has nothing to do with the graph, these points on the graph. You leave that graph alone. Work with the points. So this is the point, and this is the point, 5 versus 420 that we had. But where is the voltage at the open circuit, which is the no load voltage at the intersection where these two are intersecting? So these two guys were intersecting approximately somewhere there, which is approximately this is just a little bit above the 600, just a little bit, a point above. Remember, a box represents 10. So this is just in between. So this is 610, a box. So this point is not at 610, it's like in between. So this is approximately somewhere at 605. Okay, just at this point above. So this is where you've got your E naught, which is your no load a voltage, which is your E naught. In this case, it was at approximately 605. So you take it straight to the voltage. So that was going to be at what? At 605. So therefore, our E naught is 605 volts. The speed has not changed. It is still at the same speed that it was before. So it is the same as the previous question that we had. Do not confuse anything there. Nothing has changed. We do not have the critical resistance, just like the previous question. This time they are saying we need to determine the voltage, but look what is happening on 2.22. If we are still on this condition, if the speed is increased, take note, it has increased to 660 revolutions per minute from the 600 revs per minute where it was originally. Now it has increased to 660. And we are also given the resistance at that moment to be at 72. The concept of the resistance, which is our shunt field resistance, to be 72 ohms does not change. Change in voltage over the change in field, that part does not change the slope. What has changed is the graph. It is the graph. This graph is no longer applicable. It was when the speed was 600. This information here, it was when the speed was 600. But it has changed. So you need to create, you need to have another table for this speed, showing just like the previous case, the current and the voltage. So we are going to have, guys, another table. So I just hope, guys, sorry for these measurements which are showing. I don't know why do these softwares just don't update so that we just have like align with all these things that they are showing us. All right, so this is what I'm trying to say. I'm just gonna have a sketch here. You had the current before, which is your field current. You had the current before. That was our current in amps of field current, and the EMF, which is the voltage that you're given. This was taken at a condition like the current is not gonna, this current, these values are not gonna change. It is the voltage. Remember, okay, let me explain this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so there we've got an extra which we do not need, no problem. So this is what I want you to note. Remember, from the properties of a generator, talking of a DC machine, which is our generator, there is a relationship that we consider in terms of the speed. E is equal to K times the N, which is the speed and the flux. Considering that this K is a constant, and remember, we are still on the same machine. What changed is the speed. The flux is still the same. Taking this K, because the K is the constant and our flux 1 is equal to flux 2, you are going to see that the relationship is going to be E1 over E2 is equal to N1 over N2. We have got calculations actually on our DC machine where we consider the speed. When you are given two conditions, there is an initial condition and the second condition where there is an increase. So what we need to know in this case here is how the values are going to change. How are these values going to change? That is the condition. So we are going to make E to the subject. Guys, we are not worried about this. You can have, if you want, you can calculate, there are actually two ways. You can calculate the percentage change. The percentage change is equivalent to the difference. Remember, the speed is 660. So the difference, 660 minus 600, there's a difference of 60, which is the increase. So the percentage increase is going to be 60 over the original value, 600 times 100%. So you're going to obtain an increase of 10%, meaning to say the speed increased by 10%. But that we are not worried about that. We are worried about the voltages. So from this, we are going to make E to the subject because the speed has changed. So let's make E to the subject. Cross multiply. That is going to be E1. N2 is equal to N1 times E2. We want to make E to the subject at the speed of 660. So divide by N1, divide by N1. So this is going to give us E2. So meaning to say, on each and every condition, E2 is going to be given as the product of E1 times N2 over N1. So this is what I'm trying to say. When the voltage at the original point, when it was 100, it is no longer at 100. It is changing. There's an increase. So the voltage also changes. So meaning to say we are going to calculate E2 is equal to when E1 is 100. The speed, remember, N2, now the speed has increased to 620. Originally, it was at 600. So N2 is 660 over 600. You multiply this, you're going to obtain 110 volts. So meaning to say, when this was at 100, now it is at 110 volts. The same thing, you move on to 260. When this voltage is 260, at this point, when it is 260, when our E1 is 260, what is going to be E2 after the change, after the increase in speed? That is the idea. So you're going to obtain 286. So this is 2 versus 286. So you're going to have the same thing at 390. This was going to give us 429. At 470, it was going to increase to 517. This is what you're going to have. So that's 5 at 530. This was going to give us 583. At 570, it was going to change to 627. At 600, it was going to change to 660. So this is how you calculate these, guys. You're gonna have this, you just have to substitute into the formula that you have already made the subject. At 620, it was going to give us 682. At 630, it was going to give us 693. And at 640, it was going to give us 704. So these are new values. These are new values that we are talking about. From what we have, we are considering the new values in this case. So the question is just like what we had, guys. You were given a table originally like this. This is the table that you had before. And the question is asking you to determine the voltage when the field current is 84. So it is the same thing like what we are having now. From this table, the question is determine the voltage. This is at a speed of 606. After the increase, this is, we are still at the same speed that we are given before after the increase. So we are still at the same increase that we are given before. But this is reduced to 72. So this is what you're going to have. All right, so you're going to draw a new graph from this, a new graph. So this is what you're going to have, guys. So because of these values, if you check, it was gonna be difficult again to locate this point, but they are going to mark that graph of yours, guys. Do not worry about that. So that is 1 versus 10, again, just like 110. 1 versus 110, just like what we have. This is 1. 110 is just a little bit above the 100. Remember, according to our scale, it's one box just above, so it was gonna be slightly above. That is 1 versus 110, above that point, one box above. 2 versus 286, and so on. So this was 286, 290, 286 approx. So this, guys, it's not gonna be exact. You're gonna have approximation there. 3 versus 429. You are marking these points. 410, 20, just below 430. 5 versus 583. 583. This is 90, 80. Guys, just gonna be an approximation somewhere there. 6 versus 627. 10, 20. Just below 30. That is where we can approximate at 27. 7 versus 620. Sorry, it was 660. 690, 80, 70, 60, guys. Okay, 660 is not an approximation. It's actually direct, guys. This is 690, 80, 70, 660. It's actually a direct point. 8 versus 682. Just after 680, just a little bit after 680. 693. 9 versus 693. Okay. 7. It was 6. As you see this one now. I want to go back to the 6. It was 6 versus 6, it was versus 627. I missed a point there. Sorry for that. 6, it was versus 627 according to here. 6 versus 627 and so on. So 6 is versus 627. Okay. 6 versus 627. Meaning to say this point is actually wrong. This one is also wrong, this one, because it was 5 versus 6. Guys, here I have affected a lot of points here. I have affected a lot of points. Guys, you see these softwares, and now I want to finish up. I have recorded a lot. Let me just go back here. Let's just go back to 2. 2 versus 286. Okay, approximately there. 3, 4, 29, approximately there. 4, 5, 17. 5, 17, 10. 17 is just gonna be approximate there. This is at 4. 5 versus 583. 583 is just gonna be just below 590, because this is 580, just somewhere there. 6 versus 627. 610, 20, an approximate again. 7 versus 606. 667. That will be 10, 20, 30, 40, 50, 60, somewhere there. 80 versus 682. Again, this is 10, 20, 30, 40, 50, 60, 70, 80. 82, guys, just an approximate again. 9 versus 693. This is 90, an approximation. 10 versus 707. This is 700. 707, guys, is just a slight above the 700. So it's going, you're just gonna mark points approximately to those exact points, just an approximate, then we can join. Just like the previous case, we are going to see that this was gonna be another curve which is on top. So this one is gonna be approximately on top above that other one. So draw a smooth, guys. You are supposed to have a smooth curve, not as the one that I'm having here, guys. Yours is supposed to be, I don't know how smooth can you refer something that you say this is smooth. I don't know. It's supposed to be very smooth. So this is it. They are not supposed to intersect. It's above this one. Okay, so it's because of the first graph. You see, my first graph is a little bit like outside. It's not supposed to be like that. It's supposed to be smooth. Okay, so because of time, this is what you're going to have, just a graph above this one. So let's not have a confusion. Do not have a confusion here. The first one, it was the one which was at that speed of 600 revolutions per minute. This one that we just drew now, it is the one that is operating at 660 revs per minute. So this is the one where we need the voltage, just like the previous case. We need the voltage. At which condition? When our resistance is 72. Just like the previous case, how were you finding resistance, voltage over the change in current? So already we are given the resistance is 72. So 72 over 1, like I explained, must give you that 72 ohm. But are you going to locate the point 72? Is it visible? Just like what we saw, yes, we're going to have a reference point, which is the 0, 0. Just like the previous case, our reference point, where we're supposed to start is the 0, 0. But locating 72, guys, is difficult according to this scale that we are having of 100 and this. So we ended up last in this case multiplying by 5 to obtain values which are fine. Let's try on this one to multiply by 5 and see are we going to have a multiple which is approximate by 5 over 5? The number that you use must be the same. 72 times 5 was 360 over 5. 360 is easier for us to locate. So just like the concept that I was talking about previously, just like y over x, the change in y over the change. So it's like a point xy, which is 5 versus 360. The current is 5. The voltage is 360. We mark that point just like what we were having before. But this time, it's at 5 versus 360. So this is 5, 360. You're going to count 6 boxes from 300. All right. That's 10, 320, 30, 40, 50, 60. So that's 5 versus 360. These points, they are enough. So you are going to draw a line which will meet this graph, which is at a speed of 660 from the origin, just like what we had from the 0, 0. So it must pass through this point, all right? So let's draw from the 0, 0, passing this point here to the graph that you have drawn at 660 like this. It must pass through this point like this, somewhere like that. So that's from 0, 0 like this, okay? So this one, it meets the graph which is at a speed of 660, just like what we had before when we're dealing with that one, which was at 600 and its own part here. This one, with the one which is at 660, they meet at a certain point there, approximately that point. Okay, approximately there. This is where they meet. Where they meet, this is where our always the intersection. So you're supposed to note what is the voltage at that point, this point that we are having, a point which is in between these two boxes here, these two boxes between 700 and 710. In between, if we check that point, was going to be in between those 2 points. So that is approximately at 705 volts. At 705 volts. So guys, this is the idea. This is the idea. So meaning to say at this voltage of 705 volts, we are having the speed that is where we are having the no load in this case, just like what we had at no load. But this is when the speed has increased and the resistance was reduced to 72. You still use the same consideration or the same applications in the same way that you were working with. So these are the typical questions that you're going to expect in your examinations. Do revise as many questions as you can relate. Okay, it's only that I removed the other questions, but you can relate to those other questions. So that is what you're going to be focusing on this part. Revise your gradient. What is gradient? What is it that you refer as the gradient? If you understand the gradient concept, you are not going to have a challenge on this part. So this is what we had, guys, from Maths Zone African Motives. Till we meet again.